In the previous class, we studied the procedure to generate a tag for a given sequence. However, the binary code for the sequence is what we really want to know. Therefore, we want to find a binary code that will represent the sequence in a unique and efficient manner. We have seen that tag forms a unique representation for the sequence. Therefore, it implies that binary representation of this tag forms a unique binary code for the sequence. However, we have placed no restriction on what values in the unit interval the tag can take. Some of these values would be infinitely long, in which case, although the code word is unique, it may not be efficient. To make the code efficient, the binary representation for that tag has to be truncated. But if this code word for the tag is truncated, then the question is the resulting code unique? The next question is that if the resulting code is unique, then is that code efficient? What we mean by that is how close or how far is the average length of the code away from the entropy of the source. So, let us examine these questions. We have seen that for a dyadic source, that is, if the probabilities of the source symbols are of the form pi equal to 1 by 2 alpha I, where alpha I is an integer, then the length of the code word is given by log of 1 by pi. But if the source is not dyadic, then we have also seen that a reasonable choice for this length would be Li is equal to upper flow of log of 1 by pi plus 1. Now, in arithmetic coding, each sequence is uniquely identified by the tag f tilde x. We know that this tag is a number in the interval 0 to 1. So, a binary code word for this tag can be obtained by taking the binary representation of this number and then truncating it to L bits given by this expression. So, let us look at the example which we had studied earlier. So, we have a source consisting of 4 symbols, and we use the mapping which we had studied earlier in the Shannon, Fallow, Elias coding to convert these symbols to integer random variables. And for this source, with this probability model, we can generate the binary code based on the concept just discussed. We have 4 symbols out here. So, we have the cumulative distribution function for each of the symbol. We can get a modified cumulative distribution function for this symbol as shown here. Then the representation of this cumulative distribution function in binary is given as shown here. Then we truncate this binary representation by the length which is calculated as shown here, and using that we get the code word as shown in the last column. Now, we will show that the code obtained in this fashion is a uniquely decodable code. We first show that this code is unique, and then we will show that it is uniquely decodable. Recall that we have been using f tilde fx as the tag for a sequence x. Any number in the interval given by this as a unique identifier. Now, to show that when we truncate this tag to the length Lx, which is indicated by this, is to show that this is unique. We need to only show that it is contained in the interval, that means this term is contained in the interval given by this. Now, because lower floor because this is truncated binary representation of f tilde x. This implies therefore f tilde x truncated value is less than or equal to f tilde. Now, by the definition of binary truncation we can write the following expression. If you recall, this procedure is similar to the one which we had adopted for the Shannon-Fano-Elias coding. Now, because f tilde x is strictly less than cumulative distribution function, therefore, it implies that truncated version of f tilde is less than f of x. Now, to show that truncated version of f tilde is greater than or equal to f of x minus 1, note that one by 2 Lx is equal to 1 by 2 raised to log of 1 by Px upper flow of that plus 1. This is less than 1 by 2 log of 1 by Px plus 1, and this quantity is equal to into 1 by Px. So, this is equal to Px by 2. So, we will use this relationship. So, we have from the definition of the our modified CDF, Px by 2 is equal to f tilde minus cumulative distribution function of the sequence x minus 1. So, from this we get therefore, f of tilde x minus f 1 is greater than 1 by 2 L x. So, from this relationship and this relationship which we have derived, 1 by 2 L x is less than P x by 2, we get this relationship. Therefore, what it implies that truncated version of f tilde is greater than f of x minus 1. Therefore, it implies that the code word obtained by truncating the binary representation of f tilde is a unique representation of f tilde x. Now, to show that this code is uniquely decodable, we will show that the code is a prefix code, that is, no code word is a prefix of another code word. Because a prefix code is always a uniquely decodable code, by showing that arithmetic code is a prefix code, we automatically show that it is uniquely decodable. Now, to go ahead with the proof for that, let us look at one fact, that if I have a number, let us say a number a, in the interval zero to 1 with an n bit binary representation B1, B2 up to Bn, then for any other number B to have a binary representation with this as a prefix, with B1, B2 up to Bn as the prefix, B has to lie in the interval a plus 1 by 2 raised to n. So, using this fact, we will try to prove that the arithmetic code is a instantaneous or prefix code. Now, what this implies is that if x and y are two distinct sequences, then we know that f tilde truncated value of it given by this expression and truncated value for the representation of the sequence y lie in two disjoint intervals. The intervals are given by f of x y minus 1 Therefore, if we can show that for any sequence x, the interval given by truncated value of f x So, if we can show that this interval lies entirely within the interval f x x minus 1 f x is a open interval. So, if we can show that this lies entirely within this interval, this will mean that the code for one sequence cannot be the prefix for the code of another sequence. Now, we have already shown that truncated value of f tilde is greater than f x x minus 1. Therefore, all we need to do is show that f x x minus truncated version of f x is greater than 1 by 2 L x. Now, this is true because f of x minus the truncated version of f tilde is greater than f x minus f tilde x, because this quantity is less than this quantity, and this is can be written as minus, this by definition is by 2. So, this is equal to probability of the sequence x by 2, and this we have shown is greater than 1 by 2 L x. Therefore, this code is prefix free, and by taking the binary representation of f tilde x and truncating it to L x given by upper flow of log of 1 by p x plus 1 bits, we obtain a uniquely decodable code. Now, although the code is uniquely decodable, the next question is how efficient is it? So, let us answer that question. We have shown that the number of bits L x required to represent f tilde x with enough accuracy such that the code for different values of sequence x are distinct is L x is equal to log of 1 by p x plus 1. So, L x is the number of bits required to encode the entire sequence x. So, the average length of an arithmetic code for the sequence of length m is given by p x L x summation over all x. Now, this is equal to summation of p x. L x is chosen by this expression so this can be simplified as less than or equal to summation of p x log of 1 by p x plus 1. In fact, this is strictly less than, and this can be simplified as equal to p x log p x plus 2 summation over p x. These are the summation over all the sequences. So, we get this is by definition the entropy of mth extension of the source plus 2. So, now given that the average length of a code is always greater than the entropy, the bounds on L average length of mth extension will be as follows. So, this is the length we get for the mth extension. So, the length per symbol we denote by L average, and since we are talking about the arithmetic code, we will denote it by AC. For the arithmetic code will be given by dividing this quantity by m. Therefore, we get h of Sm over m is less than or equal to L average for arithmetic code less than or equal to h of Sm divided by m plus 2 by m. Now, for the IID source, we know H of Sm is equal to m times Hs. Therefore, from this we get therefore entropy of the source L average for the arithmetic code less than equal to entropy of the source plus 2 by m. So, by increasing the length of the sequence, we can guarantee an average length of the code as close to the entropy as we desire. Now, after having studied the mathematical aspect of generation of the tag for the arithmetic code and representation, binary representation of that tag, and also having studied the procedure to decipher this tag, let us look at some of the aspects of the implementation of the arithmetic code. So, let us look at the algorithm implementation for the arithmetic code. We have developed a recursive algorithm for the boundaries of the interval containing the tag for the sequence be encoded as given by these expressions shown here, where xn is the value of the random variable corresponding to the nth observation symbol. Now, one major problem needs to be resolved while implementing this algorithm. Recall that the rationale for using numbers in the interval 0 to 1 as a tag was that there are an infinite number of numbers in this interval. However, in practice, the number of numbers that can be uniquely represented on a machine is limited by the maximum number of bits we can use for representing the number. Consider values of ln and un in the example which we had discussed earlier for the generation of the tag. So, if we examine the values which we had obtained then are shown here. So, at the step number 1, when we have received the sequence number, the first symbol in the sequence, that is 1, the lower limits are shown here, that is 0, and the upper limit is 0.8. After we have received the symbol 3, the limits are shown here. So, from this result, it is clear that as n gets larger and larger, these values of ln and un come closer and closer together. So, the difference, this 0.8, the difference is less than 0.8, and this difference is still less than this, and this difference is still less than this. So, in order to represent all the subintervals uniquely, we need increasing precision as the length of the sequences increases. Now, in a system with finite precision, the two values are bound to converge, and if these two values converge, we will lose all information about the sequence from the point at which the two values converge. Now, to avoid this situation, in a practical scenario, rescaling of the interval is done. This is done in a manner that will preserve the information that is being transmitted, and also it is done in a manner so that the encoding is incremental. What we mean by that is that using incremental encoding procedure, we can transmit portions of the code word as the sequence is being observed, rather than wait until the entire sequence has been observed before transmitting the first bit. Now, in the literature, integer implementation of this algorithm has also been discussed. We will not go into the details for as far as this course is concerned. Now, after having studied arithmetic coding and Huffman code, the question is, which is the efficient coding scheme? So, let us look at some of the points or advantages and disadvantages related to both Huffman and arithmetic coding. Comparison of Huffman and arithmetic coding. Arithmetic coding is more complicated than the Huffman coding, but arithmetic coding allows us to code sequences of symbols. Now, how well this coding scheme works depends on how it is used. Let us try to use this code for encoding sources for which we know the Huffman code. So, let us go back to the example which we had discussed earlier in today's class. For the example which we had discussed earlier, if we look at the arithmetic code which we obtain for this source is given here, and if we calculate the average length for this code, then it turns out to be 2 into 0.5 plus 3 into 0.25 plus 4 into 0.125 plus 4 into 0.125, and this is equal to 2.75 bits per symbol. And entropy for this source is .75 bits per symbol, and because this is a dyadic source, Huffman code is able to achieve this entropy. So, obviously, arithmetic coding is not a good idea if you are going to encode your message one symbol at a time. So, let us repeat the example with messages consisting of two symbols. Now, it is important to note that we are only doing this to demonstrate a point. In practice, we would not code symbols this short using an arithmetic code. So, if we encode two symbols at a time, then the arithmetic code for that can be obtained as shown here. So, these are the different messages which can be generated. For these different messages, we can find out what are the probabilities of the sequences of length 2. We can find out what is the modified CDF. We can represent this modified CDF in binary, and then we can truncate this modified CDF in binary by using the lengths calculated as shown in this column, and finally we get the code words as shown here. Now, the average length per message for this coding scheme turns out to be 4.5 bits. Therefore, using 2 symbols at a time, we get the average code word length of 2.25 bits per symbol, which is certainly less than 2.75 bits per symbol which we obtained earlier, but still this is not as good as the best average code length which can be obtained with the Huffman code, and that is 1.75 bits per symbol. However, we see that as we increase the number of symbols per message, our results get better and better. Now, the question is, how many samples or how many symbols do we have to group together to make the arithmetic coding perform better than the Huffman coding scheme? We can get some idea by looking at the bounds on the average length for the code. For the arithmetic code, the bound which we had obtained is given by this inequality . Now, it does not take many symbols in a sequence before the average length of the code for the arithmetic code becomes quite close to the entropy. However, for the Huffman code, if we block m symbols together, then the average length of the code is given by this inequality, which we had proved earlier. So, now looking at these two inequalities, this for arithmetic code, this is for the Huffman code, the advantage seems to lie with the Huffman code, although the advantage decreases with increasing m. However, it is important to remember that to generate a code word for a sequence of length m using the Huffman procedure requires building the entire code for all possible sequences of length m. So, if the original alphabet size was q and we are coding sequences of length m, then the size of the code book would be q raised to m. Now, taking reasonable values of q equal to 16 and m equal to 20, this would give us a code book size of the value which is equal to 16 raised to 20. Now, this is obviously not a viable option. For the arithmetic coding procedure, we do not need to build the entire code book. Instead, we simply obtain the code word for the tag corresponding to a given sequence. Therefore, it is entirely feasible to code sequences of length 20 or much more using arithmetic coding procedure. So, in practice we can make m large for the arithmetic coder, but we cannot do the same way for the Huffman coder. This means that for most of the sources we can get the average length of the code closer to the entropy using arithmetic coding procedure than by using Huffman coding procedure. The exceptions are sources whose probabilities are powers of 2. In this case, the single letter Huffman coding achieves the entropy, and we cannot do any better with arithmetic coding no matter how long a sequence we pick. The amount of gain also depends on the source. Recall that for the Huffman codes, we are guaranteed to obtain average length of the codes within 0.086 plus p max of the entropy, where p max is the probability of the most probable letter in the alphabet. Now, if the alphabet size is relatively large and the probabilities are not too unbalanced, the maximum probability P max is generally small. In these cases, the advantage of arithmetic coding over Huffman coding is small, and it may not be worth the extra complexity to use arithmetic coding rather than Huffman coding. However, there are many sources like facsimile in which the alphabet size is small and the probabilities are highly unbalanced. In these cases, the use of arithmetic coding is generally worth the added complexity. Another major advantage of arithmetic coding is that it is easy to implement a system with multiple arithmetic codes. Now, this may seem a bit contradictory, as we have claimed that arithmetic coding is more complex than Huffman coding. However, it is the computational complexity of the machinery that causes the increase in the complexity. Once we have the computational machinery to implement one arithmetic code, all we need to implement more than single arithmetic code is the availability of more probability tables. So, if the alphabet size of the source is small, as in the case of a binary source, there is very little added complexity. In fact, it is possible to develop multiplication free arithmetic coders that are quite simple to implement. Finally, it is much easier to adapt arithmetic codes to changing input statistics. All we need to do is estimate the probabilities of the input alphabet. Now, this can be done by keeping a count of the letters as they are encoded. There is no need to preserve a tree as with adaptive Huffman codes. Furthermore, there is no need to generate a code a priori, as in the case of Huffman coding. Now, this property allows us to separate the modeling and coding procedures in a manner that is not very feasible in Huffman coding. This separation permits greater flexibility in the design of compression systems, which can be used to great advantage. Arithmetic coding is being used in a variety of lossless and lossy compression application. Arithmetic coding is the coding scheme recommended by the Joint Bi-level Image Processing Group, that is JBIG, as part of the standard for coding binary images. So far in our course, we were concerned with properties of information sources and with transformations of sequences of source symbols into sequences of code symbols. We were able to relate our information measure to properties of information source. In particular, we showed that the entropy of a source could be used to obtain a lower bound to the average number of code symbols needed to encode each source symbol. We also use this bound to define the redundancy and efficiency of a code. We devoted our study to synthesis of codes containing as little redundancy as possible. Now, we will shift our study from the information source to the information channel, that is from information generation to information transmission. We shall see that it is not always desirable to use codes with little or no redundancy. We will be concerned primarily with methods of putting redundancy back into codes. We will also use the entropy idea to describe how we may utilize an unreliable information channel to transmit reliable information. So, from the next class onwards, we will shift our attention to information channels and the concepts related to it.